Good afternoon, and welcome to re:Invent 2022. I hope the slides that we had here so far kept you engaged for a little bit as we got started. I'm a morning person, and being from Seattle, I love to vacation at some place sunny, So a beach is perfect for me. I love dogs, and I prefer action movies more than horror. But today, I see our session is fairly full, and we thank you for joining us, especially because this is the last session of the day, and we know that you probably had a long day today. So we appreciate that you're here. I'm Varun Kamlakaran. I'm a Principal Customer Solutions Manager at AWS, and today's session is AMZ303. Which is Analytics at Scale, presented to you by Amazon Ads. Joining me on stage will be Tom Skinner, Director, Amazon Ads. His teams built the capabilities that we're going to be sharing with you today. And also, Josh Angel, he's the Principal Engineer in Amazon Ads. He's the one who conceptualized and architected these solutions. They will share with you some pretty cool solutions to the problems they face as they built this amazing reporting capability that generates more than 400 million on-demand reports every day. In today's agenda, I will talk to you about who Amazon Advertising is and why we at AWS consider them to be a strategic partner for us. I'll also introduce the ads team that's here, the ads measurement team, and their claim to fame. Then I'll pass it over to Tom Skinner. He will talk to you about how analytics is at the core of everything his organization does. He'll also share with you the challenges his teams face and the key metrics that they use to measure success. Then Josh will be on stage to dive deep into the technical solution and share with you Ads' journey in these three areas of orchestration, data applications, and reporting. Along this path, he'll share with you some lessons learned and some pretty cool concepts that they developed as they face these problems and challenges, some concepts called as data rivers. You probably heard of data lakes, you've probably heard of data streams, but data rivers might be new to you. So that's why we have Josh over here, so stay tuned. Along this presentation, there might be a slide or two that you might like. If you like, please go ahead and take pictures of them, but we request that you do so without flash. And finally, at the end of the presentation, I'll share with you how you can meet our speakers today, Tom and Josh, and also how you can get some cool Amazon Ads swag. So look out for that. So jumping right in, who is Amazon Ads? Ads is Amazon's advertising business. You probably search for a product on Amazon.com. When you got the search results, you probably see some products that have this tag called as sponsored. Or you're watching content on Prime Video or Freebie, and you've seen these ads come through. Or you're shopping in Whole Foods and seeing some physical ads that are placed in different parts of the store. Or while conversing to Alexa, Alexa may have provided a product recommendation for you. All of these products were served by Amazon advertising systems. To give you an idea of all the products that they have, please look at the screen over here. Each of these products that Amazon Ads has, it's geared towards their mission to help brands design ad experiences that delight their customers and deliver meaningful results. With the deep insights that they have, their reach, and premium properties such as music and streaming, they're able to connect advertisers to the right audience in the right place, both on and off Amazon. Now to talk to you about the team. The ads measurement team is responsible for campaign measurement and reporting across all ads businesses worldwide. They serve as the scientific center of excellence for algorithmic development in this campaign measurement space. Some of the areas that they work in are in machine learning algorithms to measure advertisers' performance, They also identify conversion events and aggregate advertising facts at scale across all of ads businesses. They also warehouse data for business intelligence. To give you an idea of the scale that they operate, they work on more than 100 petabytes of data. They generate 40 billion reports every year, and that is 400 million on-demand reports every day. They process more than 1 trillion events every week, and some of their systems work at more than 3 million TPS. I love working with these teams. There's some phenomenal engineering that happens over here, and there's some solutioning to some gigantic problems. All of you here will benefit from this talk because this is years of experience, years of efforts that's distilled into this particular session. So stay tuned. Now, to give you more details about this session, I'd like to call Tom Skinner onto the stage. Tom, please come on over.
Thanks, Varun. My name is Tom Skinner. I'm a Director of Software Development with Amazon Ads. I've been with Amazon for 9 years, the last 4 in the ads measurement organization, leading the reporting API and core infrastructure teams. Today, I'd like to talk to you about how our customers use our advertising analytics, how we measure success as an organization, as well as our partnership with AWS. I realize that our use cases may be different than yours, but I hope that you can take patterns away from what we're explaining today to apply to your own programs. In the interest of learning, be curious as an Amazon leadership principle. If you know something better or you have better ideas for us, hit us up on LinkedIn. I'd love to talk to you. Amazon's ad technology provides advertisers with tools to plan marketing strategies, serve and optimize ad delivery, and measure advertising outcomes. Our vision is to leverage Amazon's audience insights and world-class technology to deliver best-in-class advertising performance. Advertising analytics are sourced from ad interactions logged by our ad servers, typically impressions, views, and clicks. Conversion events are sourced from our operational system, such as ordering pipelines or page rendering systems. And our dimensional data comes from our campaign management systems that our advertisers use to determine what campaigns they want to serve and the metadata associated with them. Our team combines these data sources together to produce something called attribution, which determines which traffic event gets credit for the conversion. We also create more than 500 other measures that allow our advertisers to perform campaign reporting and gives them insights into their performance of their advertising campaign. Advertisers will run this reporting constantly throughout their campaign, continually measuring and optimizing off and on through the entire advertising cycle. While our data flows may seem simple, we do have some unique challenges when calculating our measurement. First of all, our reporting API powers interactive, low-latency data tables and charts, as well as large, asynchronous, downloadable reporting. During these peak events, our customers count on their systems to have the most up-to-date data. We also can't be lossy when processing our data. So everything that we compute, every ad interaction, we have to have controls in place that every event is processed exactly once, and we can't drop data or double count. We also have a unique situation with late arriving data. We have many systems, upstream systems, such as ordering pipelines, page rendering, ad serving. And so we get things like order cancellations that we have to then go back and reprocess that can happen multiple days after the original conversion event. So when these orders are canceled, we go back and we reprocess their aggregates. And finally, we look at long look-back calculations. Some of our calculations look back as much as a year's worth of data. And if you think about it, a year's worth of traffic data, every impression on Amazon is quite a lot of data that we have to compute through in order to calculate a measure. At Amazon, we believe that focusing our energy on the controllable inputs to our business is the best way to maximize outputs over time. For example, if you're an Amazon retail customer, you've seen this before with our focus on large selection, low prices, fast delivery. Our organization applies the same mental model to our development processes, and we have 6 families of these controllable inputs that we look at continually. All the development teams have a weekly review of these metrics, and they use them to guide their development roadmap. As a team, we make availability our top priority. Our systems are critical to our advertising customers. And if they're not available, our customer experience is directly and immediately impacted. At the base, we have the simple host check. Is the host available? CPU, memory, disk utilization. All of our systems have control planes and across thousands and thousands of servers. These are automatically replaced in case they're unhealthy. We also look at service availability. We compute our service availability as the number of positive or valid requests over the number of total requests. We look at query latency. As I said before, we power data tables and charts, and so our query must respond very fast. And also, we look at data age. So this is a measure of basically how old the data is in the system from the time in which it originally happened to when it is available in our reporting layer. CloudWatch makes these very easy to compute and create dashboards for us. Our customers make investment and optimization decisions based on our data. So if we have inaccurate data, they will lead to poor outcomes for our customers and bad investment decisions. Where we can, we compare data from our upstream systems to make sure that we're not dropping data, we're not double counting. We also look at our metrics across all of our customers, and we look for outliers, trend analysis, to make sure that we can inspect our critical ads measurement. Also, we have anomaly detection to prevent bad data from egressing to our customers, and when we do egress bad data to our customers and we get customer defects, we perform very deep root cause analysis to make sure the issue doesn't happen again. A system at our scale must be easy to operate without a huge burden to our engineers. We take our work-life balance of our engineers very seriously, and we make constant investments in driving down our operational load. The first measure we look at is the operational stories per engineer. We want to make sure that they're balancing the development of the new product with our investment in our operational posture. We also look at blocked pipelines that prevent shipment. We measure how many are CI/CD and how fast the code makes its way through the pipelines. High impacting issues may be hidden by large ticket queues, so we look at overly noisy alarms, execute ticket swarms to maintain as close to zero as possible in our ticket queues. And finally, we look at ticket severity counts year over year or month over month to make sure that the investments in the operational excellence is actually translating into better developer experience as well as better customer experience. Building a highly available and scalable, stable platform does you no good unless you can ship. Advertising is a fast-moving industry with both external pressure as well as internal pressure to deliver features on behalf of our customers. So we look at three major things in this area. First, we constantly measure the complexity of our system through a number of steps it takes to launch a feature. And we look to eliminate as many of those as possible. Where we can't eliminate them, we automate them. So we look at hardened APIs, and we look at the percentage of those, and we make sure that over each quarter, we keep driving those up. Ultimately, though, our developer days is our metric that we optimize towards. And we look at developer days as a key output metric for our success. We create quarterly time trials where engineers can execute the runbook, and they can automation on a set of standard steps. And we basically perform retrospectives, and this feeds into our next quarterly development cycle. A system of our scale and size requires us to have really strong cost discipline, and we have mechanisms to closely look at our hardware usage. We have a program by which we review hardware costs regularly, and we update our forecast every quarter. We look at system utilization, again, basic hardware metrics, CPU, disk, memory. We have benchmarks across Amazon. Teams that are below those benchmarks, they have cost savings initiatives that they take on to drive better optimizations in hardware. We also look at our data processing costs and our cost per user action. We make sure that they always constantly drive this down. And ultimately, we never want our costs to exceed the rate of the growth of the business. Ultimately, we're all stewards of planet Earth. And we take Amazon's climate pledge to become carbon neutral by 2040 seriously. We found that focusing on the previous set of input metrics really does reduce our environmental impact. But recently, we've been working closely with AWS and the AWS sustainability pillar for the well-architected framework to improve our carbon footprint. First, we're looking at instance type utilization. Huge benefits in Graviton, serverless, such as EMR and Lambda serverless, will drive down carbon footprint. We also are moving large amounts of our compute into regions that have historically more renewable energy, such as the Pacific Northwest. And then we also are looking at the carbon footprint tool that was released by AWS, and we're working with them to improve that on behalf of all of the Amazon customers. Advertising is an industry that has always pushed the bounds of compute. Historically, this required building custom and non-standard solutions. And while it's important, though, to understand that the same AWS technology that is available to you is what we built our system on. Engineers that I hire can take AWS training and be effective in a matter of days. If they've implemented AWS tech before, they can be immediately productive on our team. And as a development leader, that's a huge benefit for recruiting as well as developer velocity for my team. At this point, I'd like to welcome up Josh to the stage to talk more about the technical solution.
Thank you, Tom. And hello, everyone. My name is Josh Angel, and I'm a principal engineer in Amazon Ads Measurement. I've spent the last 9 years or so building measurement and reporting systems for Amazon, and I'm here today to share some of that experience and that journey with you and some of the lessons we learned along the way. It all starts with the data. We accept dimensions through an API which stores that data in Dynamo, and we typically accept time series data in manifests pointing to collections of S3 files. An orchestration system acts as the backbone for accessing and processing this data at scale. And engineers use this orchestration system to build data applications on top of it for transforming, aggregating, joining, and repartitioning this data to generate new data sets. Those data sets are then indexed into reporting engines, and then a collection of reporting APIs are used to generate reports in the forms of tables, charts, or file-based exports. Today, we're going to deep dive into some of these areas along this pipeline, and we'll talk about the various AWS services that we used and our journey along the way. Let's start with a closer look at orchestration. Every day, we utilize more than 200 EMR clusters to run an average of 150,000 jobs. We have to process trillions of events per week, and we have to process them exactly once because we don't want to overcount or undercount, since that would affect systems that rely on us for billing and accounting. Supporting late arriving data, backfills, restatements, and measurements with varying lookbacks at this scale requires highly automated systems and a very robust orchestration system. But before you can appreciate what we do today and why, it's important to reflect on how we got there. So let's start at the beginning. Many years ago, we used the tried and tested data warehouse approach. Backed by Amazon Redshift, we were able to store and query terabytes of data. Data consumers would periodically run SQL jobs to join, aggregate, and extract data from these clusters. And as the size of the data set grew, the size of the clusters grew. And as the query volume grew, the number of clusters grew. And we ran into a few issues with this approach. First, at the time, Redshift Spectrum didn't exist. And so we had to store all data on disk, even if it wasn't being queried. And this led to unnecessary scaling. We also created replica clusters to deal with the increased query volume. And this caused confusion over which cluster should act as the source of record. Furthermore, storage and compute became tightly coupled, and that led to unnecessary and wasteful overscaling. And it also created coupling between loads and queries, which caused unnecessary resource contention and bottlenecks. And finally, our clusters had to be large enough to fit all of the data into one cluster, even if it wasn't queried. And this led to us hitting limits with the node counts that Redshift supported at the time. We needed a different approach to continue scaling effectively. So we migrated to a data lake pattern. And we did that by replacing our Redshift usage with a combination of S3 and a collection of EMR clusters. Instead of loading data directly into Redshift, we used EMR clusters to transform and partition the data for storage in S3. And we used a Hive metastore to track all this metadata, since at the time Glue wasn't available yet. We managed a fleet of EMR clusters that data consumers could use for extracting and querying data from the data lake. Now, this approach resolved many of the issues we previously had. First, by centralizing storage into S3, we were able to avoid that on-disk storage. We increased our data durability, and we reduced costs. And we did all of this while ensuring we had a consistent source of record. This separation of storage and compute also unlocked more flexibility and cost-effective scaling. And finally, clusters no longer needed to be large enough to fit all of the data on them. They only had to be large enough to support a single load or a single query. This enabled us to run many smaller clusters with dedicated purpose instead of fewer monolithic ones. And this reduced resource contention and enabled us to optimize for our most critical queries, reducing their runtimes from as many as 8 hours down to as few as 4. And this pattern worked really well and allowed us to scale to store petabytes of data. However, we struggled with data age. We were able to process data through the system and get it to customers on the order of hours, but it was difficult for us to break that multi-hour boundary. So we took another look at the fundamentals. When you look at a data lake abstractly, they maximize flexibility, but not necessarily performance. As a pattern, they function by loading data files into some cloud storage, maybe typically Amazon S3, and they track that data in some catalog, perhaps AWS Glue. And you run a periodic job on some schedule, usually SQL-based, to extract and transform this data. Now, it seems obvious that using large batches, such as hourly or daily, or relying on scheduled queries can introduce artificial delays and latency in your data processing. However, even if you switch to microbatches or you trigger queries constantly, you'll still run into some other bottlenecks. For example, the queries themselves can become very large and complicated. In our case, late arriving data also required that we process data from as much as a year back, even if only a few records change, in order to ensure that an arbitrary SQL statement was correct. And even after extensive optimization, we were only able to get these queries down to hours, even after throwing lots of hardware at them. So this pattern of data lakes works really well when you want to run an ad hoc query and you don't really care about the latency as much. But it didn't work so well if, in our case, you wanted to run the same query consistently and very quickly. So we evaluated another processing pattern, data streams. So a data stream works by processing incremental events in the order they're processed or they're received. And instead of writing queries that operate over tables, you write code that operates over individual events. By processing these individual events in the order they're received incrementally, you're able to achieve sub-second processing times. Much better. And there's some popular streaming technologies available today, including Amazon Kinesis, Amazon Managed Kafka, or Amazon EMR with Spark. And at this point, we had already made use of streaming in some of our other systems, and so we attempted to do the same for our orchestration system. But after experimentation with streaming, we realized that while data streams worked well with individual specific linear data pipelines that require sub-second latencies, they weren't always well suited for running generic, branching, nonlinear pipelines that didn't require sub-second processing. Some of the issues we ran into included complex event state stores. Now, avoiding duplicates while processing events in streams requires storing some kind of event metadata. However, most streaming consumers might already have this, since a lot of streams might be processing the data and storing it in something like Dynamo, OpenSearch, or something similar, and so they may not notice this incremental cost. However, our orchestration system needed to support branching pipelines and many consumers. This would have meant many different copies of this event grain data and persisting it to many different event stores with each step. With our scale and data retention requirements, this became a non-trivial expense. Another issue we ran into was developer velocity. Creating new streams was fairly straightforward, but making changes to existing streams became more complex. We had to update these state storage systems and the streams in specific orders to ensure that no data was lost or duplicated. And automating and testing these changes was time-consuming. Infrequent or manual updates to a few specific state stores or streams is very manageable, but we would have to scale this to support dozens or potentially hundreds of streams. We knew we wouldn't be able to migrate all of our workflows to this pattern. Supporting different patterns for different data sets wouldn't have been ideal if some consumers needed to mix and match these data sets. And supporting multiple patterns for the same data sets, such as a data lake and a data stream, led to complexities around maintaining consistency. Next, we ran into some issues with fault tolerance. So a key benefit of stream event processing is that transient failures can be retried per event, and that reduces the blast radius of failures, which is actually really good. However, non-transient failures caused by edge cases or bugs, for example, could potentially have a larger blast radius because it could block processing of the stream. The sequential nature made it difficult, and unless you drop the record or block the stream or create some separate mechanism for isolating and reprocessing these events, then you couldn't deal with it. Dropping records wasn't an option. As we've said earlier, we can't drop anything. And obviously blocking the stream is not ideal either. And neither is creating entirely new error handling systems for each independent stream. Next, we ran into some struggles around our specific applications we were looking to develop with this orchestration system. We wanted to be able to perform aggregations over long lookbacks. And while that's possible with streams technologies, it typically requires setting time windows, fixed time windows. And that's a problem because no matter which fixed time window we picked, it was always possible an event could arrive outside of that time window. And once again, we couldn't drop data, so that wasn't an option. Next, we took a look at cold starts and backfills. So typically, when you create a new stream consumer, you can process previous events to catch up. However, a lot of streaming technologies may only support hours or days worth of data retention. And Kinesis has extended data retention policies. You can store your data for up to a year. However, even with longer retention periods, cold starts are still less efficient with streams because you have to process all the events in order. That includes every version of every event, and not just the most recent event. And last but not least, we ran into challenges with scaling optimally, on-demand scaling. Most streaming technologies require you to specify a fixed processing resource, such as the number of shards or whatnot. And some have, Kinesis, for example, have on-demand, but it's a separate mode that you have to toggle between. And this is great for planning for peak or a specific day or for a backfill. It's not always practical to be manually adjusting between pricing strategies for dozens of streams or trying to use that to take advantage of daily peak versus nightly lows. So to recap all of this, data lakes couldn't meet our performance demands, even after switching to microbatches and constant query execution. And data streams weren't really generic enough or scalable enough from that sense to handle all of our orchestration workflows. Even if we used microbatch streaming with Spark, we found a lot of the previous issues we were talking about still applied. Attempting to use data streams only for recent data and data lakes for backfills and restatements led to a much more complex system, challenges with data consistency, and difficulty maintaining the linkage between the two. So what do? Well, we combined various aspects of data lakes and data streams to create a new concept. Sticking with the water analogy for data processing, we decided to call this a data river. Taking inspiration from data lakes, rivers operate on microbatch data stored in S3 with references maintained in a metadata catalog. All the data remains in S3, and the files are only references to the files are stored in the catalog. This reduces the complexity of this metastore. You no longer need event grain data, which also reduces the cost and ease of updating it. And this also helps with cold starts, since we can maintain a history of these batches for sequential processing and incremental processing, or we can always just reference the most up-to-date version of the batch for cold starts to access the most efficient form of backfilling. On the other hand, taking inspiration from data streams, rivers operate by reacting and processing data as it arrives, rather than on some schedule. We also break up larger, complex workflows that operate on multiple tables into smaller, composable steps that can be chained together to form a pipeline. This reduces the complexity of each query and enables some better developer velocity by working in isolation. In terms of performance, data rivers offer a compromise between data lakes and data streams. Rivers work on batch metadata instead of event metadata, and so the state store is cheaper and simpler to develop and maintain. And we found that rivers offer performance ranging between seconds to minutes, depending on how you've configured them. And while this isn't as good as the sub-second processing times that streams are capable of, it's still much better than the hourly scale processing times we were seeing using the standard data lake approach. We believed this trade-off was well worth it. So here's an example of what a data river might look like in S3, in AWS, using S3. Our orchestration systems operate on minute scale data with the metadata flowing through the system and the original data maintained in the S3 bucket of origin. This enables us to pass metadata through the system really quickly. It also enables the original owners of the data to maintain access control over that for as long as possible, and it prevents unnecessary data copying or transmission. The batch metadata is a storage system that accepts API requests or listens to SNS topics to process and store metadata about batches in a collection of DynamoDB tables. It will then take that data and send notifications to an outgoing SNS topic, notifying any consumers of new batches or any changes in batches, which we call restatements. We pivoted from a single multi-tenant fleet of EMR clusters to multiple single-tenant EMR cluster cells, where each cell may run in different accounts and has its own subscriber, scheduler, and EMR compute resource. And all of these are managed by a central orchestration system. We can use Lambda and SQS for scheduling these jobs and EMR for executing them. We can also scale up by simply creating more EMR clusters and by launching more jobs in parallel. And this can be done in 10 to 15 minutes. So this had many benefits for us. The first was reducing the processing time of our data. It decreased from hours down to minutes. It also enabled us to have more cost-effective on-demand scaling, and it also enabled us to have much more continuous deployment, which improved developer velocity. We could automate schema changes through our state stores and all of our pipelines without worried about processing them out of order. And all of these factors together resulted in lower operational overhead and lower financial cost incurred. The journey to create this orchestration system didn't happen overnight. It took many years and lots of work, and there was a lot of lessons learned along the way. First, make sure to separate storage and compute and query from load. Second, avoid monolithic clusters if you can avoid it. Using more optimally sized clusters and breaking up your work can be a way of improving stability. Next, make sure you choose the right technology and the right pattern for processing. Sometimes data lakes might work for you, sometimes data streams might work for you, and sometimes you might need to think of a different approach. Next, break up processing into smaller batches, which may not always be event grain, and it may not always be daily or hourly grain, but find the appropriate size that makes a good trade-off for you. And lastly, this pattern of data rivers offers a compromise between data streams and data lakes, and may work as a compromise if you are looking for something in between. Okay, now that we've talked about the orchestration system and our evolution of that into a data river, let's talk about how you would build a data application on a data river and the implications of that. So we have dozens of applications running on hundreds of EMR clusters, but I'm going to focus on 2 applications today for reference. The first is partitioning, which takes batches and subdivides them into smaller files in a particular directory structure that's more suitable for use in data lakes or reporting. And the second is aggregation, which takes one or more batches and aggregates them amongst some dimensions to reduce the row count and consolidate the number of files. This reduces storage costs and improves performance, since you have to query and scan over fewer rows. But in order to better understand why these applications are important and what they do, let's first talk about how we structure a batch of data. At a basic level, batching is widely known. You process groups of data together instead of individual events. And in our case, we applied a little bit more rigor in defining what a batch means specifically. First, a batch is immutable, and it's an immutable reference to S3 files. This is important, since if an application is reading and processing data, you don't want to go changing the files under the hood, since that can cause unwanted race conditions. And the second, a batch represents a consistent fixed time window as an abstraction. This enables predictable identifiers, and it also enables detecting gaps in data quickly. Seen here, you can see an example of a batch being produced every minute. Now, I said that it is an abstraction of a time window, and that's because each event in a batch doesn't necessarily belong to that time window from an event perspective. More often than not, that batch contains data that was discovered, logged, or processed in that time window. And this is because we have late arriving data. It could be discovered later, it could arrive later, it could take time for it to be processed by upstream systems. But as long as we maintain that each event appears in only one specific batch, or any batch, it doesn't matter which specific batch it's in. But you might be thinking, if batches are immutable, and you can't publish an event or an update for an event in a future batch, how do you correct data, update, or delete data? Well, we do this with a process we call restatements. We create a new copy of the batch and replace the old one. Now, you might think append-only incremental updates are more efficient for storage and processing, and you might be right in some areas. But in our case, that also becomes difficult to maintain consistency unless you process batches sequentially. What if you get the delete before you get the create, for example? This is, the sequential processing is what makes cold starts and backfills very painful in streams. So we wanted to avoid that, and that's what this restatement process helps with. Instead of storing only the events of a stream, or instead of storing only the events of microbatches, we store both a sequential feed of batch versions as they come through the system, as well as provide access to the most recent version of all the batches. This enables cold starts to be highly efficient. OK, back to applications. As I previously mentioned, batch time windows roughly or abstractly align with log time and may not be precisely aligned to event time when the event actually took place. And that's a problem, because BI and reporting queries are always executed over event time and not some arbitrary batch time. So this is where partitioning comes in. We created a data application that splits a batch into a new collection of S3 files by some partition of event time, usually day. In addition to sending all these new S3 files back as a new batch into the core orchestration system, we also maintain a glue catalog that maps which batches and which parts of each batch go to which day or event time partition. So at this point, we now have a new set of batches, but they're really granular. They're partitioned internally by event time, but the batches themselves are still structured by log time. So the next step is to aggregate that data. As I said, this will improve performance, but it also helps consolidate all of these small S3 files into new S3 files that are truly batched by event time. We do this by accepting a batch into the aggregation application and using that glue catalog I mentioned before to expand that to any batch part files that actually contribute to that event time and producing an aggregate for that. Now, you might think this is possible with streaming and time windows, and you'd be right. You can do both partitioning and aggregation with streams, but some key differences are that with a streaming approach, the time window typically has to be fixed, and as we said, that's a problem, and it has to be executed sequentially and with some limits and parallelization. Whereas with this approach, we can process any number of batches in parallel without worrying about out-of-order updates from newer batches or older batches. OK, so we talked about orchestration, and we talked about applications. But we just have a whole bunch of S3 files still. How do we make them available for customers to query? Let's talk about reporting. So what do we mean by reporting? Well, when I say reporting, I'm referring to any type of data analysis that enables customers to view their data and draw insights from it. Reports can take many forms, but the most popular ones include email subscriptions, on-demand file-based exports, or interactive tables and charts, such as a web UI. Currently, we support interactive reporting on trillions of events and petabytes of data. And every second, we index 1.5 roughly million records. We scan 300 million records. We produce 28 million aggregated records. And we return 8,000 responses. And 99% of those responses return within 2 seconds. So how did we do all this? Well, there's a lot of technologies you can use for reporting engines. If you publish your data into a data lake, you were going with that approach, you can use technologies like Amazon EMR, Redshift Spectrum, or Athena to query your catalog. Alternatively, you can publish your data directly into a specialized indexing or time series database, such as Amazon OpenSearch or Amazon TimeStream. And there's no constraint that prevents you from mix and matching and using multiple reporting engines to take advantage of their strengths and avoiding their weaknesses. For example, Amazon Athena works really well for ad hoc requests or where you don't need low latency. But it's not really great for really low latency or really high TPS reporting at our scale. And if you want to scale to support our particular pattern of 8,000 requests in sub-second time over petabytes of data, it was a journey to get there as well. Initially, we were early adopters of Elasticsearch. This was back when it was just an open source library, before there was any hosted solutions available. And we created clusters inside VPCs and used EC2 and auto-scaling groups to separate the different node roles and for indexing and querying of data. And as we continued to grow, we created multiple clusters, up to 9, and we load balanced between them. But we noticed there were a few issues we were struggling with. It was becoming difficult to deploy and maintain multiple clusters like this. And storing data directly on EC2 hosts created coupling of storage and compute, which, as we talked about earlier, is not great. At this point, Amazon OpenSearch had just launched, but we couldn't use it directly, at least the hosted solution, since we relied on proprietary plugins, and the hosted solution doesn't support plugins or custom plugins. So instead, we turned to using the OpenSearch containers and Amazon Elastic Kubernetes service. With this new approach, we upgraded to a newer version of OpenSearch, and we used EKS containers, deployments, and stateful sets to manage all of our node groups. We migrated to using persistent volume claims backed by EBS instead of direct storage on EC2. And this enabled us to separate our scaling for storage and compute, which allowed us to optimize costs and reduce those by as much as 10%. This separation and to EBS had another benefit, which is we could replace our EC2 hosts, and we didn't trigger the expensive data replication tasks, since the EBS volume would move to the new host within a matter of minutes and bind directly. We were able to get all of this functional prototyping up and running in EKS within a week, using EKS-CTL, which is the official command line interface for EKS. And through a combination of scripting and CDK, we were able to fully automate our cluster creation process. This reduced the time needed to spin up new clusters or update them from weeks down to hours. This unlocked the ability to run many small clusters instead of fewer monoliths, and it reduced resource contention amongst some of our most critical queries. And that reduced operational issues, and it increased performance by as much as 50% by reducing latencies for our P99, for 99%. Today, we manage 24 and growing production clusters powered by thousands of hosts using this system. So what were some lessons learned along the way here? Well, unsurprisingly, there was a lot of lessons that overlapped with the orchestration journey, since we learned these in parallel. The first, make sure to separate storage and compute, load from query, again. Once again, avoid monolithic clusters and opt to use more optimally sized ones. Choose the right technology. There's many viable reporting engines, and depending on your performance needs, some might work better than others. And lastly, container-based solutions, such as EKS, can be a good way to replicate multi-component stacks very quickly and programmatically. So now that we talked about how data is indexed, how do we generate the actual report? Well, calculating a single aggregated value, a table, or a chart from a technology like OpenSearch is fairly straightforward, and you can do that with a single request. But what about really large file-based exports? What do we do there? Well, depending on the request parameters and your data set, there could be millions of rows, and the export could take anywhere from seconds to minutes. Even if you're using an engine that natively supports millions of rows, such as Athena or EMR, there are other aspects to consider. What about creating a stable interface abstraction, or supporting localization, or human-friendly formats, such as Excel? Well, why don't we talk through our API? First, we'll start with the API gateway, when a customer makes a request for a file-based export. It goes through a load balancer, which then connects to an ECS container powered by Fargate. When a user makes a new report request, it creates a new entry and a Dynamo table. From there, a Dynamo stream listens for new records in this table and starts the reporting workflow. This workflow will then create a task entry, which then gets planned and broken up into multiple smaller steps. These steps are then executed and managed with step functions. The first step that is very likely to execute is report generation, where reports are broken down into smaller parts and executed in parallel. An example of how a report might be broken down is, instead of one large report over hundreds of campaigns, perhaps it's hundreds of smaller reports over one campaign each. All of these execute as steps, and all of them produce computer-friendly file formats, such as JSON, for their individual components. And this is useful since if there's any transient failures, only that small subset of the report has to be retried. And if you're processing exports that process millions of rows over several minutes, you really don't want to start all over again if something happens to your network. So the next step is to package all these part files together and produce a complete result. Now, this might include combining all of them into one file. It might include converting that file into a human-readable one, such as CSV or Excel. And it might include localization, depending on the customer parameters and locale that the customer is located in. At the end, this final file is saved in S3 and communicated back to stable storage, where customers can then download it. Now, this entire process can take anywhere between seconds to minutes, depending on how large the report is or what the parameters are. And you might think, by looking at this, some of the components seem unnecessarily complicated, but all the components do serve a purpose. For example, the many instances where you see SQS or Dynamo streams instead of direct calls are a good way of decoupling services from each other and smoothing out load spikes. Another example where you might see something kind of odd here is the combination of both Lambda and Fargate. Now, Lambda is really good for triggering asynchronous processes, such as listening to SQS queues and triggering some kind of action. However, it's not always great for sub-second response times because it may require a cold start, and it's not always capable of running for really long periods of time. So that's where, in some cases, we'll use ECS with Fargate. So some lessons we learned along the way with reporting APIs, as we just talked about, was choose the right technology. Once again, this pops up. And in this case, you'll want to learn the pros and cons of the various AWS services, and you'll probably need to combine many different AWS services, maybe even some that appear like competition but aren't, such as Lambda and Fargate. You may want to use Lambda for your simple asynchronous processes that take a short amount of time but aren't latency sensitive, or Fargate for your really latency sensitive front-end services, or for your really long-running processes that can take several minutes to execute. Another lesson here is, once again, process data in smaller batches. This enables you to break up big, complex workflows into smaller pieces that enables better developer velocity because you can work on those pieces independently, and also enables better retry policies since you can retry those individual components. So to recap, we talked about orchestration workflows using rivers and how to build partitioning and aggregation applications on a data river. We also talked about how we built a high TPS, low latency reporting engine and evolved it with EKS and OpenSearch, and how we used step functions and many other AWS components to build a scalable and resilient reporting export system. I hope there was a pattern or two that you can reuse in your systems, or some lessons that we learned along the way that you can accept as well. Thank you. I'd like to welcome Varun back on the stage.
Thank you, Josh. Wrapping things up, right? I'd like to know how you can meet our speakers today. They're going to be in the ads booth. The ads booth is in the Venetian Expo. It's booth number 2040. They're going to be there tomorrow from 4 to 5 p.m. So please join them there. There's also going to be snacks served, and there's plenty of swag that's going to be given away at the ads booth. So please do visit the booth there. And thank you so much for joining our session today. And we greatly appreciate your feedback. So if you can provide your feedback in the app, that'll be very helpful for us. Thank you, everybody. Take care. Have a wonderful rest of the day. Bye.